Very good. Good to see you. We are back. Chapter 15, part 2. Doing the last couple of reactions for this chapter. We did alkane halogenation last time, and we'll review that at the beginning here a little bit. But this is meant for Friday, April 10th. Homework 15, though, is due the next Monday, so it's not due tonight. And then we're getting ready, of course, for test 4. We'll do a review video available on Monday there. And remember, sample test 4 is already on Learning Suite. You can be looking at that. We'll mainly work problems from that or any other ones that we might be able to help you out with. And then test 4, of course, through 15, chapters 12 through 15. So 12 was what? The reduction oxidation chapter, mainly the oxidations of alkenes and alcohols. We focused on that. And then 13 was mass spec and IR. 14 was NMR, we just finished. And then 15 here is our last chapter. That will be the multiple choice exam. It'll be posted on Learning Suite. It needs to be uploaded by that Tuesday night. Okay. We'll also have a review video for the final as well coming up. So we've got a couple more to help you out with. Let's move over here to the board here to review our alkane halogenation. So we've got a couple examples here to review. If you want to work these problems and come up with the products, that's what we have to do, the reactivity here for this. And this is always the most important thing to keep straight when we talk about reaction. What's the reactivity? The combination of the starting material, the reagents, the conditions it's exposed to, and then what are the products? So kind of make sure you keep track of that independent of the mechanism. Use the mechanisms, of course, to help you keep these straight. But this is the level of understanding you need that's very important, I think, the reactivity. So we've got chlorine with this alkane. We've got photolysis conditions. We have a photon of light here. We're shining light on it. We're at room temperature. What does that mean then? We're going to do monochlorination. But there's going to be different products, right? So hopefully you came up with this product. And if we chlorinated this methyl, that would be the same on this isopropyl fragment. And we'd also have what? This chlorine. And there wouldn't be much selectivity there. Remember, the two propagation steps for chlorination are both exothermic. So there's enough energy to breach those barriers as well here. So again, we're just showing the different possible constitutional isomeric products. And then what else we got? We got the methylene position there. So it's secondary chloride, primary, tertiary, secondary chloride. And is there one more here? So hopefully you came up with how many products? Let's see, there should be, I think, 4. So yeah, so also this one right here. That's a distinct primary chloride from this first one here. So hopefully you can see the connectivity there. So expect 4 products. We don't expect you to calculate the approximate or the exact percentages from each one. You can actually approximate that from the relative rates and weight that with the average of the number of hydrogens in those sets. But we're not expecting you to go through to that, but the 4 products are. Now, contrast that with bromination conditions. So bromine and light here, what are we going to get? We're just going to get one product. Why? Because bromine's highly selective, much more selective than chlorination, because the steps are endothermic for the propagation steps. But the reaction goes cleanly, and remember for bromine, you always just find the most substituted carbon. That's usually methine or a methylene, not a quaternary carbon. You need to put the halogen on there in place of a hydrogen, so that primary one is the only product. Now, here's a chiral alkane, right? That is the stereocenter. Yeah, there are 4 different groups on here. Don't forget the hydrogen in the back. So I think that is what, R? Yeah, that's the R. Stereocenter, we're brominating it, so the same conditions there. And what's going to be the product? Well, the product is going to be brominating at that, the methine position to give us the tertiary bromide. And notice now what happened to our R stereocenter. It went away. And that's because the intermediate radical here at the tertiary position is flat, right? sp2 hybridized. So that the probability of bromide coming on from the top or the bottom, and that second propagation step, you might want to review the mechanism there. But it's not R or S, it's what? A mixture of the two. So it's say a racemic plus minus or a DL pair of enantiomers. Okay, so that's a good review, I think, with a little more complicated substrates there. Let's go on to our next topic now, which is going to be radical reactions with alkenes. And the difference here is going to be allylic substitution and anti-Markovnikov addition. We're going to have a couple of distinct conditions here. But generally, when we talk about reactions with alkenes here, we can either add a radical to the alkene, you get a new carbon radical, or we can abstract at the allylic position here. Remember, this is allylic. This is a vinyl position here, right on the alkene. But another carbon here that has this allylic hydrogen, if we have some sort of a radical here, we can take off that and form what the radical allylic system here. And that has a resonance structure, right? We can push the electron over here to this carbon position. And the true structure, we could say, is this delocalized radical. Okay, so those are depictions of all of them there. And with the simplest case here, the two sides are degenerate, they're the same, but not so with different alkene substrates. So we'll have to look at this. Now the conditions that we can do this reaction with involve NBS, N-bromosuccinimide, and light. Again, shining light on it like we halogenated alkanes. Light and at room temperature, okay? And we're going to do monobromination here, and we're going to get the allylic bromide product, okay? Now remember what NBS is, N-bromosuccinimide, okay? Where did we see this before, NBS? Let's see if you remember that. NBS we saw before when we did halohydrin reactions, bromohydrins, when we reacted NBS and water with an alkene, okay? That was doing a heterolytic process with carbocation intermediates, with a bromonium ion. We can form a bromonium ion from NBS, but if we're under radical conditions here with light, the room temperature, or if we use peroxide initiation, that's not a pair of old-time glasses, that's oxygen-oxygen bond between two terp-butyl groups. So either one of these conditions will shunt the NBS toward a radical pathway. We'll look at the reaction here in a second, and we'll get allylic bromination from it. NBS, don't worry about the succinimide. It comes from succinic acid, which is the dicarboxylic acid with 4-carbon So the metabolite we'll see later on in 352 and in biochemistry. It's in the citric acid cycle. But right now we have the nitrogen-bromine bond that can be broken either heterolytically when we did a halohydrin reaction or homolytically under these radical conditions. So we'll have to modify the mechanism of how we deal with that. Let's look at some other conditions here. NBS, before this was developed, we could also use molecular bromine, Br2, to do this if we kept the concentration of bromine very low. Now notice we used bromine before, Br2, to what? Form the dibromide of alkenes, okay? But here, if we have bromine dripped in slowly to a solution, and we're shining light or having peroxide, you still need these conditions if you're using molecular bromine to do this in place of NBS, okay? That changes the mechanism over to the radical pathway and gives, instead of the dibromide, it gives the allylic bromide. So we're going to have to review some of these bromine-containing reactions here at the end of the chapter to keep these straight, because we've covered a lot of different halogen reactions, especially with bromine. But let's look at some products here from this process first, then we'll get into the mechanism. So NBS and light, and that's really all you need to show. You have to show the light, okay, to do the radical thing here. And what we'll get is the allylic bromide, okay? So bromine at that allylic position can be formed quite easily. Let's see. How about if we have this alkene? Now, this one's a little more complicated in that the allylic radical intermediate is not symmetric now. We have a secondary position, and if we do the resonance here, the allylic thing from this substrate, we'd have a primary thing here. So with NBS and light here, we can get this product, and we can get what? We can get double bond moved over here. And I guess we could also get the cis product here. Okay, so there's a couple different products there. This is at that secondary position, the allylic radical. This would be at the primary position, and isomerizing the double bond over. So the three different products there are a possibility. Now let's look at one that's just a little bit more complicated. And you can see here there are rules to figure out, which one of the primary or secondary ones you will get. We're not going to hold you to that. If you do this allylic bromination with a more complicated alkene, just pick all the different products. So and that's kind of bad because before we've only had you, draw the major product and get full credit. But this is a rare case where you should consider all of them. And in general, they are all formed, which makes the purification difficult here. Usually these allylic halogenations are just done on simpler substrates. And we are limited to bromine here because it is endothermic for these steps. We'll see on the mechanism here in a second. Well, let's look at this one. So if we have an alkene like this, for example, how many products can we get? Well, let's kind of look at the allylic radical. We can have that allylic radical, or we could pull the hydrogen atom here and get this allylic radical, right? So when we form the bromides, we can either form the bromide here, the secondary position on this one, or we can have what? The primary position on that one. So those would be the two resulting products from this radical. But what if we have the radical mechanism start over here? We get this one. We'd also have this product. Let's see, we could say, well, what if we have it on the other side here? Well, that would be the same thing. Are there a couple other products we could form here? Yeah, both the cis here and the cis here. So that's a possibility of 5. Draw those out. So there's a problem there with this selectivity. Let's look at the mechanism here of the process, and let's just look at the graphics in the book. I think that's good for this reaction. What have we got up there? So looking at the mechanism, we have NBS homolyzing now, right? So for shining light on it, we can break that bond with electron going toward bromine and electron toward nitrogen, and we get this stabilized nitrogen radical. You don't need to worry about nitrogen anymore from that point. It can dimerize or terminate on its own, but let's see the rest of the reaction here. So we generate a bromine radical atom, atomic bromine. And that can actually grab another bromine off another NBS and form Br2. It's actually a complicated process here. But if we have bromine radical, let's see what it can do. On the alkene at the allylic position, it can abstract or react with that hydrogen atom and then form the carbon allylic radical right here and HBr. Yes, the reaction does get acidic. Okay, so the byproduct here is HBr. Just like we saw, HCl or HBr is the product of alkane halogenation as well. So that's similar there. Now the allylic radical can react with NBS again, and that's okay. If you want to show the allylic radical grabbing a bromine atom off NBS, that's okay. It's showing it from bromine. Now, where did bromine come from here? Well, like I said, bromine radical up here, this initiation step, could grab more bromine atoms from NBS. So you see why this mechanism is complicated. The key thing here, though, is the allylic radical. And if you have an unsymmetrical alkene, like the ones we just showed on the board, you can get the resonance here, of course, and then you can put the bromine on either side. This one's symmetric, so it doesn't matter which one you do it on. So this is a complicated mechanism. It's actually kind of controversial. We got a lot of different things here, like the fate of the NBS nitrogen radical. What happens to that? Don't worry about it. Okay. In fact, I've never put this mechanism on a quiz or a test. The reactivity of it's the important thing. Well, at least the intermediate, the allylic radical intermediate is the important thing. Now, the other reason why this is important has to do with this effect right here. So what are we talking about here? Well, here are our fats, acyl triglycerides. We've talked about these fatty acids or these fatty esters. We've talked about saturated fats, stearate, and palmitic acid. We've talked about monounsaturated fats, like this one here. This is oleic acid, so at the diene position is a cis-alkene. That's a very common, very abundant monounsaturated fat in nature, both in animals and plants. There's a higher preponderance of polyunsaturated fats, linolenic and linoleic acids with 2 and 3 double bonds. And of course, we also have arachidonic acid, which is a 10-carbon long-chain fatty ester, which has 4 double bonds. Now, the problem is here, at these allylic positions shown in blue, oxygen can actually react. It reacts very slowly, but oxygen in the ground state, O2, sometimes we draw it as a double bond. But actually the most stable form of oxygen in the ground state is the triplet form, where there's 2 radicals on each oxygen. So what can occur here, if these collide together, you can have an oxygen here from O2, abstract a hydrogen atom, and give this stable allylic radical. Okay? Now that's a problem because more oxygen can combine there and form a peroxy radical, okay? Forming the carbon-oxygen covalent bond. And then this peroxy radical can propagate this chain process and grab another allylic hydrogen atom and make more what? Allylic radical. Plus, this product here, this hydrogen peroxy allyl species, can then cleave and form different products like electrophilic aldehydes and unsaturated aldehydes. Those can form covalent bonds with DNA and proteins and cause all sorts of problems with inflammation, macular degeneration in the eye, and other issues characteristic of heart disease or even cancer. So this effect of oxidizing at the allylic position can be a problem. And it's this allylic radical here. Now in nature, most of them are cis here. If we have these partially hydrogenated fat materials in margarine and other food products, where we hydrogenate polyunsaturated fats to make monounsaturated fats, a lot of times the monounsaturated fat left behind is of the trans geometry. Those trans fats actually undergo this allylic oxidation even faster than the naturally occurring cis ones. That's part of the reason why dietary trans fats are more dangerous for you and are more correlated with LDLs, low density lipoproteins. We talked about the transports for these fat molecules, including cholesterol, but also these fats are not water soluble and have to be transported in those vesicles. Anyway, there's one other topic here. You can actually quench these allylic radicals and stop this damaging pathway, this oxidative pathway, if you could put a hydrogen atom back on that allylic position, even after oxygen initiates the thing. How could we put a hydrogen atom back on this allylic radical here? Well, there are antioxidants in nature. There's a number of them, different vitamins, glutathione and acetylcysteine, and the phenols, vitamin E, vitamin C. There's also proteins that terminate these allylic radicals that can be problems. Superoxide dismutase disproportionates the hydroxy peroxides that are generated. So there's a lot of natural pathways to correct this oxidative thing going on. But we live in this oxidative environment here on Earth. We have a high percentage of oxygen in the air we breathe, and this oxygen over time, this is a slow reaction, fortunately, and these repair mechanisms are there. Let's look at one of the repair mechanisms here that comes from vitamin E. The vitamin C, maybe I'll write that on the board in a second here. There's also these food preservatives which cut down on the decomposition of unsaturated fats. BHT, or butylated hydroxytoluene, has this phenol hydrogen that can quench the radical. And you see vitamin E also has this phenol. Let's look at vitamin C maybe on the board here as well. So do we have vitamin C? No? Okay. I know the structure. Let's come down to the board here. How do we quench these allylic radicals? So you see how it's similar to the pathway of this. So if we have O2 here, we can have this. We can have the allylic radical, right? So there we've got our radical. And a vitamin E and vitamin C can quench this allylic carbon radical. Vitamin C has this structure. Let's just draw that real quick. Vitamin C is the water-soluble radical quencher. 1, 2, 3, 4, 5, 6. And 6 carbons, yep. And at this position here, you see we can grab that hydrogen atom, and it's that hydroxyl right there at the beta position. Notice this is a enol, an unsaturated alcohol, and I'll show you why. We can go to this, which now has that hydrogen back on there. That one just came from the vitamin C. And then the vitamin C, you see, ends up like this. It has an oxygen radical there, which is resonance stabilized. We've got the ability to draw a resonance structure here and put the radical there, or the radical out on the oxygen, okay? And there are ways to quench this radical naturally and go back to vitamin C, but the same effect of the phenol compound. So if you have vitamin E or BHT, the food preservative, you see you can abstract that, and then you get the phenol stabilized oxygen radical, where you can draw a resonance structure with the radical here, here, or here, okay? So it kind of ties into resonance effects. And which bond is the weakest bond here? This bond is the weakest oxygen-hydrogen bond that can react in a radical pathway to give this stabilized guy and give back the unsaturated fat without the oxidative damage. So that's one of the pathways in the body to correct that damage. Okay, I think that's enough on allylic radicals. Allylic bromination is the key reaction there with NBS or bromine, Br2, kept at a low concentration, and light there. Okay, let's go on to the next reaction here, which is going to be radical addition to alkenes. This is going to be the anti-Markovnikov addition here. So if we have a radical, we can also do this type of thing, right? We can add and whatever this X group is and get a carbon radical here instead of the allylic hydrogen atom abstraction. So this is a different set of conditions. It's going to be an alkene, of course, but HBr. And we are limited to HBr. We're going to be shining light on the system here. Okay, we've seen HBr before when we did hydrobromination way back in chapter 10. But now we have what? We're shining light on it. Or we've got peroxide. Okay? So you can just draw the terbutyl peroxide, or just say peroxide initiation there. It doesn't matter. And what we get out here is addition of bromine and hydrogen, both of them across here, and we get the bromo product. Well, what do you notice about this product now? This is HBr. We've done that reaction before, right? HBr on its own is hydrobromination. And what product did we get? Did we get the same propyl bromide in that case? No, we got the secondary bromide. And we call that what? The Markovnikov product. Now that's the heterolytic pathway, right? Involving cations and bromine anions. Our electrophile in that case was H+. This is a strong acid after all. But now we have different conditions. HBr with light or peroxide, we get what? The anti-Markovnikov product. Okay? Now make sure you switch that over. And what that means is, now with the primary product in place of the secondary in this case, the mechanism must be very different. We've got a different set of conditions here, okay? Let's look at some examples of this. It's anti-Markovnikov pathway, and then we'll get into the mechanism, of course. It's not that much of a departure, though. But let's look at our different products here. So HBr, light, and make sure you have light there. If you don't have the light, you're getting a different product. But if you've got the light now, you're going to get the anti-Mercaptan product, the primary bromide in this case. Let's see, how about this one? If we have benzene here, with this alkene here, HBr, all of these will be HBr and light. What do we get? Phenol for the benzene, I'm not just going to draw that again, and the bromine right there. Before, if we just had HBr without that, we'd get the what? Tertiary bromide, okay? Because that's where the carbocation would be. So obviously, this is a different type of product. How about this one? We have this one. What's going to be our product with HBr and light? We're going to get bromide there. Don't forget about the methyl right there. We got a choice here, primary versus tertiary. They gave the primary product exclusively. That's the only product under these conditions. How about this one? How about a tri-substituted alkene? Yep, under these conditions, you're going to get the secondary bromide in place of the tertiary. Okay, very different. How about this one? We've got it on a ring here. We're going to put our bromide at the less substituted spot, the anti-Mercaptan spot. The hydrogen is going to go here. But oh, look, we're going to have stereo center. And so, what are we going to get here? Actually, we're going to get both cis and trans. Okay, and both of those are chiral actually. So both of them are a DL pair. You know, I want to draw them out there. So I'm going to total product. Both of these are stereo centers now. This is a complicated one. So actually 4 different products. 2 cis's and 2 trans. Okay, that's how we keep track of it. Remember, 2 to the n power, how many stereo centers are there? So that's 2 to the 2 or 4. Let's look at the mechanism now. Maybe we'll look at the one on in the book, which is fine. Let's switch back over here. Isaac, thank you. So yeah, the different mechanism, right? We've got initiation here with light or with our peroxide, okay? So let's see, peroxide, if that does the homolysis there, we get 2 oxygen radicals. The R refers to the carbon framework. Tert-butyl is fine if you want to stick with that specific one. A lot of different peroxides are known here, and all of them will initiate this reaction to give the anti-Mercaptan product. So here's our first step, the O radical interacting with the HBr. Now there's a couple ways this could go, right? How come we're forming the oxygen-hydrogen bond and forming an alcohol product here in this first step? We could take the oxygen and grab the bromide. It's an alternative pathway. Why do you think we're doing this one and forming the alcohol product? Well, if you remember from bond dissociation energies, that's over 100 kcals per mole. Okay, and the probability of grabbing a smaller atom, the hydrogen, is faster there. An oxygen-bromine bond is very weak. It's even weaker than an oxygen-oxygen bond. So the oxygen-hydrogen bond is a more stable one, and that generates what? The bromine radical. The bromine radical then enters the propagation steps here, which involves what? Bromine adding to the alkene, like we talked about in our generic step. And it's going to add what? From the less hindered side and form the more substituted radical. So it's going to add on this end here where the 2 hydrogens are and put the radical at the secondary position. There's a methyl over here, right? So it's adding on the end. And then we've got the more substituted radical. Remember, they parallel the stability of carbocations. Tertiary, more stable than secondary, more stable than primary. So the basis for the anti-Mercaptan competition is that, again, we're adding the electrophile on the end position. And this radical is electrophilic. So it's really the same mechanism. The difference now is it's a different electrophile. HBr on its own to give the Mercaptan product without initiation, radical-wise. There, the electrophile is what? The proton, the H+. So in a way, it's really the same mechanism if you want to look at it that way. But anyway, okay, secondary radical here. And then the next step here is more HBr. And there we have a choice also. Carbon-hydrogen bond is formed. Why? because the carbon-hydrogen bond is more stable than the radical grabbing the bromide part. That would form another carbon-bromine bond. And that would kick off what? A hydrogen radical. That would be unstable compared to a bromine radical. Here we form the carbon-hydrogen bond in the second propagation step. And notice here, bromine radicals are chain carrier. These two propagation steps are in a chain process here. Once we do the initiation of the radical pathway, these two steps go until the starting materials are consumed, okay? So it's a similar mechanism that way. But you can go back, and all those other examples that we showed on the board previously, you could go through that. Now, this is limited to bromine. Does not work with HI. Okay, iodine radical would be endothermic in this first propagation step. Carbon iodide bonds are just not stable enough to carry this reaction. Does not work with chlorine because the second step for chlorination is endothermic because of the stability of HCl relative to HBr. And we don't do fluorine because fluorine is very exothermic for forming carbon-fluorine bonds. Those things just detonate and explode. So we don't deal with that. So we're limited to bromine here with HBr to do this anti-Markovnikov addition. But make sure you've got the right product there selectivity-wise. So yeah, here it is blown up. You can see it a little bit better there. So the radical addition step is here. We put the electrophile, the bromine radical, and I'm calling him electrophile because it is electron deficient. It's not bromide anion, right? This is bromide with 7 electrons around it. So it wants an electron out of that alkene. It'll generate the secondary radical. Here, this is what? This is our original reaction from what? Chapter 10. This is hydrobromination, where our electrophile was the proton here. This is without radical initiation, okay? So we put, what, the proton, H plus on the N carbon there, to generate the more stable intermediate, the secondary carbocation scheme. So in a way, these are really the same mechanism, but in different pathways, both heterolytic pathway here with HBr, generate cations and anions, bromine anion and the carbocation, whereas here is the homolytic pathway. Okay, very good. Review that by comparing those mechanisms back to those other intermediates we saw there. All right, the last topic here. Let's see, what if we leave out the reagents and just take an alkene and initiate it with some radical initiator? What if we have an alkene here and we're going to initiate this with peroxide and light? So we don't have NBS, we don't have HBr, we don't have anything else except a catalytic small amount of the initiator, the radical conditions, and an alkene. What are we going to get? Well, was this a mistake? We're going to get no reaction? What's going to happen here? We have ethylene gas, and if we bubble that into a solution with a radical initiator and shine light on it here or heat it up, it forms product, and it forms it actually quite quickly. And we're going to form what? We're going to form polyethylene. So here X can be hundreds or thousands of units long. And by X, what we mean here, it's just a portion of the polymer product. The alkene is the monomer, the initial part. And you can see here's one monomer unit, here's another monomer unit, another monomer, another monomer. I think there's 4 units here, 4 units of monomer represented in the polymer. And this is a solid material. If we do this carefully, we have high density polyethylene, HDPE. Some of these acronyms you need to know. Okay, polyethylene, PE, you should be aware of that one. We'll see what? PS for polystyrene here in a second. And how about PVC? That's maybe one you've heard of before. You don't need to be a plumber to know what that one might mean. PVC, what is it? Polyvinyl chloride. Yeah, another very important polymeric building material. And so we've got a couple here, and you can see the units there. But how did we get there? I guess we need to figure out the mechanism of this. And, you know, we left out the reagent. Well, what do we get here? We've got the initiator, Okay, and we got the alkene. We don't have any HBr or NBS, so we're not going to do, antimarkovnikov addition here. Well, ethylene would be the same, right? And there's no allylic position. We don't need to worry about that. But we've got the initiator. And what can it do? Well, it can add, okay, to that and generate this, which would have our initiator and radical. Okay. Now remind yourself that's addition to the pi bond, and we're creating a carbon radical from the oxygen radical. That's actually a favorable thing. And we're making a carbon-oxygen bond. That's favorable as well. But we only have a catalytic amount of that, tiny amount of that. So what else do we have here present? Well, we have more alkene. So what can occur here? Well, add some more. So what do we get? The initiator part's there. And we just added another monomer unit. I think you can see that, right? And then we can add some more, right? And some more. So let's just go ahead and keep polymerizing here until we get to a polymer. We can add hundreds or thousands of these units until we get to what? Will this just continue to infinity? No, there's a practical limit here. What can happen is what? At the end, we can add more of the oxygen radical to what? Terminate the chain reaction, we call it. Or if we have any oxygen in there, oxygen can terminate the thing. Or we can actually have an abstraction of one of the hydrogens on the end, which will terminate and put an alkene on the end. So sometimes we get a lot of different things going on. Actually, low-density polyethylene is this irregular polymerization, which actually gives branches. We could form radicals on the polymer chain and then have branch units start to polymerize off. That leads to low-density polyethylene. We're not going to go into all that. We're not going to go into the engineering of these things, polydisperse and monodisperse polymers and viscosity. It's big areas of study for polymers. We're just going to look at a few of the different ones. We're going to look at polyethylene, and how about polypropylene from propene, and what were the other two I told you about? Polystyrene. So styrene is vinyl benzene. Styrene is this whole molecule right here, vinyl benzene. It's just another name for styrene, so if we could polymerize that. And what was the other one? Oh, polyvinyl chloride. Let's just look at a couple of these. Let's get rid of the mechanism here and see what they look like. So there would be polyethylene where we got. Polypropylene would look like this. Where notice every other carbon has a methyl group on it. They skip each other. Okay? So 1,3 skipped for whatever the alkene unit is right there. There's where the monomer units are in the polymer. And you can see polypropylene. We have the initiation step. Oh, I kind of drew this the other way around, didn't I? So the initiation would go like this, and you draw out the secondary unit there. And then we'd have what? More of them polymerizing this way, because then you'd always want to generate what? The secondary radical position there. That would be more stable. You wouldn't want to add the initiator here and then have the primary radical. Okay, so we're kind of building it from the other side there. You can see the skip thing, right? The methyls will be 1, 3 to each other. Same thing with polystyrene. There we just have a phenyl group here and phenyl there. And notice if we add the unit there, we'll have this benzylic radical. Okay, this radical at the secondary position on styrene, we can delocalize that into the benzene ring. And that's a very stabilizing effect. So polystyrene. Or rigid polymeric material, and you can blow air into it, make foam materials, polystyrene foam, styrofoam, it's called, right? Okay. Polypropylene tends to be a little softer material. Polyethylene, depending on how it's polymerized, can be high density or low density. Yeah, polystyrene, a little more rigid with the 1,3 benzenes. And then what? Polyvinyl chloride will look like this. So do polypropylene. And so I guess we could just put Y units here for the different polymers, right? If Y equals a methyl, that's polypropylene. If it equals what? A benzene, that would be polystyrene. And if Y equals a chloride, that would be polyvinyl chloride. Okay. That's probably all you need to know. But be able to go between both the polymer and go back to the monomer. Okay, so if you see just a straight chain of all carbons here, you know it's polyethylene. If you see a straight chain of carbons with alternating methyls, that's from polypropylene from propene. And if there's alternating benzenes or chlorides, that's the other polymers. So, or the other monomers that correspond to the polymer. Anyway, so the reactivity part about it, I think is enough there. Let's go back to the overheads here and see what else we can see there. I think we got a couple applications, and don't worry about these applications depending on how they're made and how mono or polydispersed the materials are. How long the chains are and how uniform they are affects the properties, of course. Here's PVC1 application of these blood bags and tubings, medical tubing. Of course, you can also add a white dye material. I think it's titanium oxide to make the white plumbing pipes, polyvinyl chloride, which are very rigid. They persist for a long time. In fact, they're more durable than iron-based pipes. Okay, so plumbers like PVC piping. This is a lot lighter. It's easier to joint them together and to cut those tubes. So plumbers love the stuff. As long as you don't hit it or hard or anything. Yeah, it probably has worse mechanical properties there, but lifetime and how it persists, PVC is very, very durable. In fact, these polymers are victims of their own success. If they're thrown away and put in the landfill disposal, the garbage, whatever, they persist for thousands of years. They don't break down readily. So that's a big problem in the environment, these persistent alkene polymers. There are other types of polymers that degrade more readily, like the polyesters. We'll talk about those in 352, and the polyamides or nylon. We'll talk about that later. Here's a PP for polypropylene. These more rigid syringes here. I think I showed you that drink cup that had the PP top to it. And here's a unique one, I think, polyfluoroethylene. There you go, a straight chain here, where fluorine is taking the place of all the hydrogens on polyethylene. This is polytetrafluoroethylene, or Teflon is the trade name here, which is the non-stick material. Does not like oil or water. It can be coated on the porous metallic surfaces and make non-stick cookware and other non-stick surfaces. It's made into dental floss as well. Some other applications there. I think I showed you the dental application. Let's go back to the board. I don't think I have it on there now. Let's go back to the board here to finish up just real quickly a couple of other polymers, which are these acrylate polymers. I think I showed you one of them, the introduction to this chapter. So here's one here where you've got an ester and hydrogen, a methyl group there. So this is methacrylate monomer. And if we have the initiator here, and let's do a different initiator. Let's do the one with the blue light used in dental applications. So here's our initiator, actually with blue light here. Doesn't look like peroxide, but if you excite this with an electron here, the actual structure is this. This is the excited state of the material. Kind of difficult to draw there. But there we are, the excited state. And it looks like that oxygen diradical. So it kind of looks like the terbutyl oxy radical. And if you could excite this, right, there you go. There's the diradical here. When the blue light can do that, I think it's 350 nanometer light. So that's the blue gun here. And this is in the matrix of the material used to do the onlays, the adhesives, whatever. So once this acrylate sees this initiator, you can get the polymerization to start here. So let's see that. Let's have the initiator. And what do we have? We have the ester. And yeah, we got the carbon radical there. So the oxygen radical added on the end of the acrylate. And then I think you can see here, we've got more ester, and I'll just say E there for a bunch of them. And what do we get here? When we look at the polymer, well, we've got this. And let's see, we've got ester there, and methyl, don't forget about the methyl that's there. So there's one monomer unit, and then it skips. Here's the terminal one that has 2 hydrogens on it, and then more ester, more methyl there, and then another unit here, and another there. So I think I got, what, 3 units there? So this would be the stuff that would stick the onlay to your, what's left of your natural tooth material. It's porous material. This material in the liquid form will fill all those holes, and with the blue light, it will polymerize and solidify that onlay and correct that cavity, whatever. And this happens in seconds. This curing process, as it's called, involves this radical polymerization of acrylate alkenes. Okay, that's probably enough there. Just another quick application there. I'd like to review here in the last second. Well, I've got a couple reviews to help you out with here. Well, let's get them on the board. Let's do it sequentially here. Let's review first a bunch of these reactions from chapter 15. Let's see where we're at here. So how about this reaction? Well, let's do chlorine, excess chlorine, and heat. And then let's do chlorine 1 equivalent and light. And then let's do bromine 1 equivalent and light. And then down here at the bottom, let's do cyclohexane, the bromine, light. And then let's not stop there. Let's do t-butoxide and then MCPBA. So there's your bonus thing, a couple of sequential steps there for a synthesis application. And what about this one? Let's do cyclopentene, methylcyclopentene, NBS, and light. So this is the reaction from today. Let's see how we're on that. And let's do this one, same conditions, but with 2 butene. And let's take that and react it with sodium cyanide. So another multi-step thing here. Let's take 1 butene and react it just with HBr. Okay, so let's compare this hydrobromination thing. And let's do the same substrate with HBr and what? Peroxide. Okay. And let's take the same set of conditions here and react it with this alkene. Okay. And we got a couple more here. I'll put them up here after you do these. So see if you can do those. Pause the video if you want. See if you can go through this. All right, we're back. Let's see here. We have excess bromine or chlorine and light here. Okay, what are we going to do here? Well, we can put a chloride on there, and we can put a chloride here. Okay, now that's just monochlorination. Those are the only 2 monochlorides because of the symmetry here. But if we have excess in heat, what else can we form here? We can form dichlorides, right? We can form trichlorides. We can form tetrachlorides. We can keep going up and replace every hydrogen in this molecule if we do it long enough. And with heat here in excess chlorine, we can eventually get to all chlorinated products that will generate a lot of HCl also, but these over-chlorinated products are going to come from these type of conditions. But if we just use 1 equivalent here in light, which one are we going to get? Well, it's still not selective with chlorine. We will get some of the one there, but I'll also get mainly that one. Why? Because we have a lot more primary positions with chlorine. Now, don't worry about the ratio or calculating how much of what. I think this one is the major one, though, just because there's a lot more primary hydrogens in here. Now, contrast that with bromine. What are we going to get with this substrate? We're going to get the one product, the tertiary bromide. Okay. Now, how about this one here? We're going to get the monobromo. And that's the good thing about bromination under light conditions. We just get the one. Okay. And then t-butoxide, what are we gonna get? Elimination, yeah. So there's a way to go from the alkane to the alkene with those two steps, right? And then we can make all the other reactions, right? The reactions from chapter 10 and the reactions from chapter 12 that we learned, right? So NCPBA here, we're gonna form the epoxide, okay? All the way from the alkane. That's a powerful combination of conditions there. How about this one? NBS and light. Well, we're going to get the allylic bromination. Going to get that one? Is that the only one? Nope. We can get a mixture here. That one. Oh, are those the only two? Don't forget about this up here. So we could also get what? This one. Bromine, sorry about the size there. Oh, not there. Not there, okay. So, and those are the symmetric positions there. I think there are 3 products there. Check that. I think there's just
you go there too.
Oh, what about down there? Isaac says, yes. We can also get this one. Oh, there's a lot here, sorry. Is that the only one there for that? Oh, no, I think there's one more.
Oh,
How about that one right there? Once we have that allylic resonance, we can also get that one. Oh, how many there? I think there's just 5, maybe. See if you can come up with another. Oh. And that's a problem, right? You have this allylic position here, you have this one here, and you have this one here. I think those are the only 3, but they generate different products, right?
I think there's one more product actually.
Is there one more? Where is it?
If you put the radical at the top of the cycle and then do the resonance.
This one here?
Then do a resonance structure.
I think that's this one. Is it that one?
Oh, the opposite of that then.
And then that would be the same product, I think.
Oh yeah.
I don't
Right.
know.
Okay. So,
Double
yeah.
check that. Isaac
That's
thinks there
right.
might be 6.
No, I think you're right.
I don't know. Okay. How about this one though? This one's a little more straightforward. I think we get the 2 products here. Well, now we get that primary one and we get also this one here. Now if we react actually this mixture with sodium cyanide, what? This is SN2 conditions now? So which one's gonna react faster? Oh, primary one, and it's allylic, yeah, so your major product would probably be this primary cyanide right here, with this one reacting faster. Actually, this one can also react with SN2 prime mechanism, so a lot of that will react over, and mainly this primary position will be the major. You'll get some minor product adding it to 2 position there, but this one would be the major. But don't worry about that, it'd be a mixture. But I think you should be able to see how you get to that with the combination of the 2 reactions. All right, HBr on its own now. No radical initiation there. What do we get? This product and that product only. If you show the primary product here and say, oh, it's a mixture, we'll have to take off points. This is the major one, okay? But if we do the radical initiation here, we'll get the what? The anti-Markovnikov product, okay? So those are 2 different products from the 2 different conditions there. Okay, make sure that's straight. Same thing here, radical conditions here, this last conditions there with this alkene, what are we gonna get? We're gonna get that primary bromide, okay? I think I had like 1 more here. Okay, 2 more, sorry. A lot of reactions. Let's see, how about this one? Cyclohexene with a methyl there, HBr, and peroxide. What are we going to get here? Where's the bromine going to add? It's going to add right here, right? Not here. That would be the Markovnikov. Anti-Markovnikov's there. So we're going to get what? The H there and the bromine there. Okay, stereocenters. How many different products? I'm not going to draw them out. You can. There's going to be 2 cis and 2 trans again, because of the 2 stereocenters. They're both stereoisomers. They're a pair of enantiomers, I think. And then the other combinations are what? Diastereomers of each other. So that's a nice one to review those concepts if you need to. Okay, what about this? Styrene and peroxide and light. What's the product? That's right, polystyrene. So should be able to draw a couple monomer units. Styrene, styrene, styrene. Oh, I think I need another carbon there and then the bracket right there. So make sure you have the bracket correctly there, and you have 2 carbons per monomer unit. Now our polymer can extend here with hundreds or thousands of units there with alternating benzenes on each one. So polystyrene, there from styrene. All right, last thing, sorry, might be going over a little bit. How many reactions involve bromination? We've covered a lot. Bromine was selectively used in this chapter for the anti-Markovnikov hydrobromination. It was also used for allylic bromination with NBS or bromine at low concentration. But bromine has been all over the place in chapters 10 and 11. Let's see if you can think of all the reactions we've learned this semester involving bromine. And keeping these straight, so this is kind of reviewing for the final, but I like to point these out now in chapter 15 because the bromine reactions are just overwhelming. Okay, I have to draw them out to keep them straight, so don't feel bad here. Let's start out with the one we know, hydrobromination of alkenes. That's chapter 10, I think. You should know that problem. What was the other bromination action? Well, just bromine itself. That gives the dibromide of that. And let's combine this with bromine now, low concentration, or NBS, and light. So just with that alkene there. So we've got a different one there. Oh, what about this one? Bromine and water. Let's see if we can come up with that one. What about bromine with alkanes? We've got bromine and light here, okay, with alkanes. Was that the only alkane reaction? And we'll just stick with propane or propane here. Let's see if we can do this. Let's see, what was another one we needed to do? How about HBr and peroxide? Okay, so there's your anti-Markovnikov. Oh, don't forget about alkynes. We've got bromine, Br2. We've also got HBr on propine. Let's see, how many is that? 1, 2, 3, 4, 6, 7, 8. Is there 8? Think back through chapter 10 and 11. These two are chapter 11, I think. And these are chapter 15. We got a couple from 15 there. But if you want to pause the video now and see if you can think of some other bromine reactions or come up with these products real quick. And this will help you keep track of them or review them. This is good review for the final. So what do we have here? We're back. HBr, just the alkene alone. What do we get? That's right, secondary bromide product. Br2, though, with an alkene, what do we get? We get the dibromide. Okay? Different reagent, different products. Okay? What if we have Br2 here, low concentration, or NBS and light on it? Well, we don't mess with the alkene. Well, actually, it's the allylic radical intermediate, but we get the allylic bromide product. So that's different. And I like to put these two right next to each other, though, to see the difference in reactivity. And then what about Br2? Or we could use NBS here. That was the other spot we had NBS. And this is chapter 10 again, right? And water, so this is a halohydrin, or bromohydrin reaction. And what do we get here? We get out the bromide on one and alcohol on the other carbon. Which is which, though? Let's see if you remember. That's right, we put the electrophile, which is bromine, out on the end, and what? Water attacks at that spot. That's where more positive character is, so that's where the alcohol is bromohydrin. So 4 different products there. Yeah, keeping those straight can be tricky, but look at what's in the reagents, what's over the arrow that tells you which is which. Same thing here, beginning of chapter 15. What do we get? Just put it at the more substituted spot. Okay, so that's with the alkane. Those are rare reactions with alkanes, right? Then we got HBr under the antimark products. Yep, less substituted one there. And what do we get here? We have two equivalents. What do we get? We get that's right, the tetrabromo product. Okay, we have two pi bonds there in an alkyne, and with excess bromine, we can get out the tetrahalo product. Same thing here. If we have two equivalents of that, what do we get? That's right, two bromides at the more substituted spot. The electrophile, the H plus, goes out on the end. Okay, so we'll do some more reviewing. We'll combine some of these reactions from 15 with spectroscopy to start out our review, but then we'll review and do sample test 4 in our next video. So stay tuned for that. Very good. We'll see you next time. Thank you.